Hey y'all, welcome back. Today we're using Riemann sums to estimate the area under a curve. And really what we're doing is learning how to evaluate definite integrals. So number one says the graph of the velocity of a car traveling on a straight road is shown above. A table of values at 5-second intervals is shown to the right of the graph. So we've got the table and the graph. These are both trying to showcase the same information, but one's tabular and one's graphical. Okay, the first part of this question says, during what intervals of time is the acceleration of the car positive? So the acceleration will be positive when the slope of the velocity is positive. Okay, when the slope of the velocity. So what we're looking for is the velocity needs to be increasing. Okay, so this is going to be a lot easier to see on the graph, I think, than the table, although you can kind of see it on the table too. But we can see that the graph of the velocity is increasing between 0 and 35, and then also between, that looks like 45 and 50. So those are going to be our two intervals here. Let's scoot this up a little bit, hopefully not too much because I want to be able to see the graph on the next section. But yeah, so during what intervals of time? The time intervals are going to be between 0 and 35, and also between 45 and 50. Now, as far as the reason for our answer, we're just going to state that the slope, because the slope of the velocity is positive. You could also say that the velocity is increasing. Both of these essentially mean the same thing. You're welcome to use either one of those explanations, whichever one makes more sense, but we do want to reference the velocity since that's what's given. Okay, part B says find the average acceleration of the car in feet per second squared over the interval 0 to 50. So what we're looking for is the average rate of change of the velocity. This is the rate of change of the velocity. So so to calculate this, we're going to go ahead and take a look at what the velocity was at 0, and we can see that it's 0. And then take a look at what the velocity was at 50 seconds, and then just use our good old-fashioned slope formula. Let me zoom out a little bit so we can see everything. So yeah, the average acceleration is going to equal 72 minus 0 over 50 minus 0. That's going to be in feet per second squared. So we're just going to get 72 over 50, and that's going to reduce to, what would that be? 36 over 25, and that'll be in feet per second squared. Part C says find one approximation for the acceleration in the car at t equals 40. So we're looking at t equals 40. That's going to be, I'm going to highlight this right here. Okay, that's the velocity, but we want to estimate the acceleration. If we're looking at t equals 40 here, basically what we're wanting is the slope of the tangent line, the line tangent to the curve at that point. In other words, we're going to estimate, let me get a little smaller thing here, we're going to estimate the slope right here. So it says find one approximation, and that's because there's a couple of different ways we could approximate this. We could approximate it from the left, meaning we're going to like pick these 2 points and find the slope there, or we could approximate it on the right-hand side, okay, finding the slope between these 2 points, or we can use a symmetric approximation and find the slope between this point and this point. So either one's fine. You just use one of them, and maybe I'll show you all 3 of them, but I kind of wish I could see everything. I'm going to have to really zoom out here on this one. Okay, so let's just like break down each one so you'll know if you got it right or not. Hopefully you worked this out ahead of time. But let's try the left approximation first. Again, you only need one of these, but I want to show you like the different acceptable answers. So the left approximation would be the approximation given the point to the left of 40 and 40 itself. So in other words, we're going to use the time at 35 and the time at 40. So that would be 75 minus 81 over 40 minus 35. 75 minus 81 is going to be negative 6 over 5. So yeah, negative 1.2 feet per second squared. Okay, so that's one good approximation. The right approximation would be if I picked the point at t equals 40, this one right here. So same point we used before, but then the point to the right of it here. So the right approximation is going to be, we're going to use t equals 40 and t equals 45. So to calculate that, we're going to have 60 minus 75 over 45 minus 40, which is going to equal, would that be negative 15 over 5? That's going to be negative 3 feet per second squared. So that is an acceptable answer. And then I'm kind of running out of space here, but the symmetrical approximation would be the approximation if I were to use, instead of using 40, using 35. Oh, that's an ugly arrow. 35 and 45. So I'm kind of out of space here, but maybe I'll work it out to the side here. So the symmetric approximation would be 60 minus 81 over 45 minus 35. 60 minus 81 is going to be negative 21 over 10. And so that's going to be, we can't reduce that. That's going to be negative 2.1 feet per second squared. So all three of these answers would be right, but you would be expected to get at least one of these, okay, or really only one of them. You don't need to give me two different approximations. It just says find one approximation. But I wanted to work out all three here that you could potentially get so that whichever one you ended up using, you could check to see if you did it right. Okay. Letter D says find the midpoint sum for the data. Okay, midpoint sum for the data by using midpoints of the five subintervals by using the midpoints of five subintervals of equal length. Use correct units and explain the meaning of the answer. Okay, let's go back up and take a look here. Let's split up this data into, what was it, five? Yeah, five subintervals of equal length. So we're going from 0 to 50. If I'm going to split that up into five subintervals, let me erase all this. Let me go ahead and put my right boundary, my left boundary here, and I'm going to split that up into five intervals. So the first interval, or each interval, I should say, is going to have to be 10 units long. So like I'm going to have a partition 0, 10, 20, 30, 40, and 50. So that's 1, 2, 3, 4, 5 intervals. So we'll go from like 0 to 10, from 10 to 20, 20 to 30, 30 to 40, and 40 to 50. Now this particular question, I think it said the midpoint one, right? The midpoint sum. So what we're going to do is use the midpoint of that interval to as the height of the rectangle that we're going to construct. So the first one is going to be this rectangle. The second one will be this rectangle right here. The third one will be right here. Notice I'm using the midpoints of the interval to figure out how high the rectangle should be. Here is the fourth one. And here's the last one. We're actually going to use this one down here. Okay, so as we're figuring out like what the height is, it's always going to be that point in the middle when we're doing the midpoint sum. So these values right here, like 5, 12, 15, 30, 25, 70, 35, 81, 45, 60. These are going to be the heights of those rectangles. Each one is of 10 units long. So like my first, let's go ahead and I wonder if I can fit it all on here. I'll just go ahead and start computing it. Okay, so we've got 10 times 12, plus, and actually, let's just factor out that 10. Maybe not. Maybe we're not there yet. Plus 10 times 30, plus 10 times 70, plus 10 times 81, plus 10 times 60. This arithmetic's a little tedious here. Well, actually, we're multiplying by 10, so it won't be too bad. But if this were any more complicated, you could probably expect it to be on a calculator section. So you get 120 plus 300 plus 700 plus 810 plus 600. So let's see if I can't knock this out make this a little bit more efficient. 300 and 700, that's going to be 1,000. Let's see, 810 and 120 is going to be 930 plus 600. So that's going to be 1530. So that's going to be 2,530 feet. Okay, now what this represents, maybe I'll wait to box it here because I want to explain what this means. This represents the change in position in feet. Let's go ahead and use the units here. In feet from 0 to 50. Okay, another way of thinking about it is that it's the displacement of the car. Okay, how far is the car away from where it started at the beginning? And let's take a look back at that graph. Like, what are we actually doing here? Okay, we're finding, this area underneath represents like how far the car moved. Okay, if we multiply feet per second by seconds, we're going to get feet. And so one way to start thinking about these integrals is as an accumulation function, where you're just like adding the unit, which is the integral of your y value, or in this case, velocity. You're just adding what you've accumulated from the beginning to the end. Okay, so you're like adding all this area, sort of one rectangle at a time. So yeah, it's the change in position or the displacement of the car from time equals 0 to time equals 50. Letter E says find the left Riemann sum for the data by using 5 sub-intervals of equal length. Indicate units of measure. So we're going to basically do the same thing, except instead of using these midpoints, we are going to use the point on the left of the interval. So I'm going to erase all these rectangles here, but keep my partitions. Okay, since we're still doing 5 intervals, we're going to leave the partitions where they are. But instead of using these midpoints over here, we're going to use the left-hand partition of each interval. So I'm not going to use these. Instead, I'm going to use these. So 0, 10, 20, 30, and 40 as the heights of each rectangle. So the first one's just going to have a height of 0. Okay, this point right here is at 0. The second rectangle is going to have a height of 20. The third rectangle is going to have a height of, 55. The fourth rectangle will have a height at 78. And the last rectangle will have a height of 75. Okay, so again, each length is, the width of each rectangle here is 10, right? And I'm going to just keep track of these heights over here. So I'm going to have to keep this on screen. But my setup's going to be just like part D. I'm going to have 10 times 0. And you might just not even write that, but I want to try my best to keep track of each rectangle. Plus 10 times 20, plus 10 times 55, plus 10 times 78, plus 10 times 75. Okay, let's zoom in so we can do this arithmetic. So we've got 0, that's the area of the first rectangle, plus 200, plus 550, plus 780, plus 750. So 0 and 200 would be 200. 200 and 550 would be 750. So you have 750, another 750, and a 780. 750 and 750 would be 1,500. And 1,500 plus 780 is going to be 2,280 feet. And again, that's still talking about the change in position in feet. So we've got basically this other estimate, right? And these estimates, they're not like, super close. They're a little close, this 2,530 and 2,220. Again, these are just estimates for the area under the curve, okay? The more rectangles that we put in there, the more intervals that we divide this graph up into, the more accurate these estimations are going to be. Okay, that's enough for number one. Let's take a look at number two. This is not going to be a full page problem like the last one. So number two says the graph of f over the interval 1, 9 is shown in the figure. Using the data in the figure, find the midpoint approximation with 4 equal subdivisions for the area under the curve and bounded by the x-axis. Okay, so here's 1, and let me count to 9, which I assume is the end, but just to make sure, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now the distance between 1 and 9 is 8. So if we're going to divide this into 4 equal subdivisions, then each partition needs to be 2 units long. So I'm not going to draw my rectangles yet. I'm just going to draw in where my partitions are going to be. And then if I'm using the midpoint approximation, I'm going to pick the value of the function that is in the middle of each partition. So like for example, the height of the first rectangle will be found right here. The height of the second rectangle is here. The height of the third rectangle is here, and the height of the last rectangle should be here. So let's draw those rectangles. Here's the first one. Here's the second one. The third one, and finally, the last one. So we're going to multiply 2 by each one of these. Now you might be noticing, like on the last couple, that you're doing times 10, times 10. We're multiplying all those 10s. Here we're multiplying a bunch of 2s. It's okay if you want to just go ahead and factor that out. Let's say 2 times, and then just add up all the heights. So you can do it separately like we did up here, where we just do like base times height plus base times height plus base times height. But since all those bases are going to be the same, you could just kind of separate that out. So I'm going to have 2 times. The first height is 1, 2, 3, 4, 5. The second height is, let's see, 5, 6, 7. The third height is 7, 8, 9. And then the last height, I think, is 6. 1, 2, 3, 4, 5, 6. Yeah. Okay, so we've got 5 and 7 is 12. 12 and 6 is 18. 18 and 9 is 27. So we have 2 times 27, which is 54. That's not 57, 54. Number 3 says a test plane flies in a straight line with positive velocity in miles per minute at time t minutes, where v is a differentiable function of t. Did I say that right? V is a differentiable function of t. And then we've got some selected values. Okay, so this question is asking us to find a right Riemann sum. So instead of picking the midpoint like we did over here in the previous problem, we're going to pick the value of the function that is on the right of the partition, or like the right-hand partition of each interval. So if we want 4 subintervals, we need to divide this into 4 equally spaced out intervals. And so since the time goes from 0 to 40, right, 0 to 40, we're going to, if we divide that by 4, we get 10. So each subinterval should be 10 seconds long. So basically, like, our partitions are going to be at 0, at 10, at 20, at 30, and 40. And the heights we're going to be using are going to be the right-hand partitions. So for the first rectangle, we're going to use 9.5. For the second rectangle, we're going to use 4.5. For the third one, 2.4, and for the last one, 7.3. So let's go ahead and compute this. So each subinterval is 10 units long. So we're going to have 10 times 9.5 plus 4.5 plus 2.4 plus 7.3. So let's see, what would that be? Or I guess should say approximately. So that would equal, let's see, 9.5 and 4.5. That's, let's see, 13. That's going to be 14 plus, that'd be 9.7. Yeah. So 14 and 9.7 is going to be 23.7. So times 10 will be 237 miles. This is also asking us to explain the answer in terms of the flight of the plane. So the integral of velocity's position. So this is going to represent the plane's displacement. I had some trouble with my pen here. The plane's displacement in miles from time 0 to time 40. And that's in minutes. So basically it's saying, how far did that plane end up compared to where it started? Okay, let's move on to number 4. It says water is removed from a tank at a rate modeled by capital R, and it's measured in liters per hour, where R is a differentiable and decreasing on the interval 0 to 8. Selected values of R are shown at the table below. When time is 0, there are 50,000 liters of water in the tank. So the first one says estimate the derivative of R at 2. So we don't have t equals 2, so we can't pick like the left approximation and the right, or the right approximation. On the very first problem, we had a little bit of freedom there. That was like 1c, where we could pick either one because we did have that middle point. But here, because we don't have that middle point, we have to use these two to make that approximation. So the slope of function r at 2 is approximately 950 minus 1,190 over 3 minus 1. So let's see, 11 minus 9, that'd be 2. So 240 over 2 would be, and that should be negative, sorry, negative 120 liters per square hour. All right. Part B, use a trapezoidal sum with 4 subintervals indicated by the table to estimate the total amount of water removed from the tank during the 8 hours. Now with the trapezoidal sum, like if we kind of envision what's going on here, let's go 0 to 8. And I'm not going to draw this to scale or anything, but all these R values are decreasing, right? We've got 1340, 1190, 950, 740, 700. Maybe I need to go a little further here. And when we calculate the trapezoidal sum, we're trying to find the area of these trapezoids. This one, this one, this one, and this one. Now, the way that you find the area of a trapezoid is you multiply the height, or in this case, the width, by the average of the bases, which in this case, the bases, like the B1 and B2, are these vertical segments. So we are going to average the height of each one of these points and then multiply by the difference between these t values. Okay, so let's kind of break this down a little bit. So these points are going to be at 0. These are not even equally spaced here, but that's okay. 1, 3, 6, and 8. And to find these areas, we're going to average the R values. So the average R value, or like, add them up, divide by 2. I won't calculate it on my head. Let's write it down. So the first one is going to be 1 that's the length here, 1, right, times the average of 1340 and 1190. So that's going to be 1340 plus 1190 divided by 2. Okay, so that's the area of the first trapezoid. That's the area of this one. The area of the next one will be 2, because that's the length of this one, times the average of 1190 and 950. Okay, that's the second one. The third one, this interval is of length 3, so we're going to do 3 times the average of 950 and 740. And finally, the last one, this interval is 2 units long, and the average of the R values, 740 and 700. All right, there's our setup. We're going to have to do a little arithmetic here, so bear with me. We've got 1 times, let's see, 1340 and 1190. That would be 2530. Do a little quick math here. 2530 divided by 2 is going to be 24. That's 12. Carry the 1, 6. Did I do that right? Gosh, I really hate to have to break out the calculator here to check my work, but I want to make sure this is right. So Mr. Schuler is going to go off to the side and actually do this division separately. And okay, good. Yeah, that's correct. So 1,265. Okay, the next one is, let's see, 1190 and 950. 1190 plus 950 would be, let's see, 2140. 2140 divided by 2 would be, gosh, let me think. Wish all these numbers were even. It'd be 10, 14, so no, what would it be? It'd be 1,000, 1,070. I'm going to have to go to the calculator just to make sure. Yeah, it is 1,070. Okay. I'm going to be checking myself with the calculator here off to the side because I want to make sure these numbers are right. 950 and 740 would be 1690. 1690 divided by 2 should be 845. Yeah, 845. I'm imagining this is probably going to be a calculator problem, if I'm being honest with you. Here, 740 and 700 is going to be 1440. This one's going to be pretty easy because the midpoint's going to be 720. So, yeah, 2 times 720. All right, so I'm running out of room here, and all we're doing is just multiplying and adding. So, I'm not going to have really enough space to work this out without a calculator. I think it probably is doable. You know what? Nah, let's do this without a calculator. So the first one is 1265, right? It's times 1, so I can just leave it like that. The second one's 2 times 1070, so that'd be 2070. No. See, maybe I should use a calculator. 2140. Oh gosh, 3 times. Okay, never mind. I'm gonna use a calculator here. 3 times 845. I don't have the patience for that. That'd be 2,535. And then finally, 2 times 720 would be 1440. All right. So now I just need to add up all those. And y'all, I'm giving up. I'm tapping out here. I'm going to use a calculator for sure. 1265 plus 2140 plus 2535 plus 1440 is 7,380 liters. Yeah, I feel like this is a little bit too much arithmetic to really expect you to do that without a calculator. It's not impossible, but these numbers are just getting pretty big, and I would think I wouldn't be too mad if you broke out the calculator too, because I sure know I just did. Okay, let's see if we can't get the rest without a calculator. C says use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Now, what we got in part B represents the total amount of water that was removed from the tank during the 8 hours. So what we need to know is how much water was there originally. And that was given in the prompt. It says at time equals 0, there are 50,000 liters of water in the tank. So if we want to know how much is left, all we need to do is just subtract 50,000 minus 7,380. So let's see, 0, 2, okay, the 1. Oh, no, this is, okay. You know what? It's too late in the day to be doing this kind of, I just want to make sure that my arithmetic is correct here. So, yeah, I'm going to type this in. So I get 42,620. Okay, and what this is, the units are in liters. So this is how much water is left in the tank. Number 5, the function f is continuous on the closed interval and has values shown in the table below. Using a right Riemann sum with 4 subintervals, and the intervals are given to me, what is the approximation of this integral? So because we're using the right Riemann sum, we're going to pull the values for f from the right-hand side of each interval. So from 3, 5, 8, and 10. The first subinterval has a length of 2, and the height is 12. So actually, let me just make the whole statement here. The integral from 1 to 10 of f of x dx is approximately equal to 2 times 12 plus, let's see, are they all 2? No, yeah, this is 2, this is 2, this one's 3, and this one's 2, so be careful. 2 times 16 plus, run out of space here, so I'm going to drag this back over. Oh, nope, this is not going to let me. Now it's going to want me to take all those. That's okay. Plus 3, because from 5 to 8 is actually 3 units, times 23, plus 2 times, bring it in just a little bit more, 17. All right, 2 times 12, that's 24. 2 times 16 is going to be 32. 3 times 23, that'd be 69. And 2 times 17 is going to be 34. So we need to add 24, 32, 69, and 34. And I'm getting 159. What are our units here? Oh, we don't have any units. So it's just 159. Our answer is D. And that wraps up our tonight's homework. Y'all, thanks for watching. Please reach out if you have any questions. I know we're getting to the point where calculus is getting a little complicated now. So please, I welcome any and all questions you might have. So please reach out if you do. Otherwise, y'all, thanks for watching, and I'll see you next time.